So let's talk about substitutions. Substitutions are to integration as the chain rule is to differentiation. So chain rule, substitutions, very much related. So here's the theorem. Here's the fancy textbook version of it. If u is some differentiable function g of x, whose range is in the interval I, and f prime is continuous on that same interval, then the integral of, hey, this thing should look a whole lot like the chain rule. Then this integral can be expressed as f primes in terms of u. And what they did when they made this u substitution as g of x, they took this g of x and this g of x, let me use some colors here. They took g of x and turned it into u. Okay, so if you replace the entire function with this, then now all of a sudden there's no more x in here, but there's only a u, and so the differential gets replaced as the entire derivative g prime of x. So I always found that a little bit hard to see and kind of complicated. So we're going to do examples to get to the bottom of this really, but this is just the idea to really kind of express what it is and further our idea of, hey, this the integrand is the derivative of integrations looking for the parent function that has the integrand as its derivative. So sure, that should look familiar. Like, okay, well, the formula for the chain rule is the derivative of the original function to which we applied the chain rule f of g of x, a composition of two functions. So let's take a look at this. I'm not going to teach you how to do it. I'm just going to see if we can guess our way through this. And if you look at the bottom of the slide, you see the punchline that there's a much better way of doing this, but let's just do this as an exercise. So underneath this thing, let's see what we've got here. We'd say, okay, I want to take this integral and I want to think of this as f of g of x. Let's use some colors. F of g of x times g primed of x, and then our differential dx. So our question is, what has this thing? So what has this as its derivative? And so we'll take a look at the chain rule formula. Well, the chain rule formula says take a composition f of g of x, take the derivative of it, prime it, and get f primed of g of x times the derivative of the inside guy, g primed of x. And so what we're going to try and do here is we're going to manually try to undo the chain rule, which in general is a very complicated process, and most of the time we won't be able to do this. But for this example, I bet you that we can. So let's see here. I'm just kind of look at this and say, all right, well, g primed of x, this thing right here looks an awful lot like the derivative of this guy. Right? So 3x squared plus 1 is in fact the exact derivative of x to the third plus x. So down here, we're going to say, all right, so our inside, it looks like our inside function, g of x, well, so right there, you can just straight up identify g of x as x to the third plus x, and then g primed of x as 3x squared plus 1. So now what is left? What's left is to say, okay, well, what does f do? Well, looks like the only thing left there is that fifth power. And so math's favorite generic variable, slap an x in there, just like we would do if we were doing a chain rule here, and say, all right, well then f primed of x would be, oh, wait a minute. Wait a minute. I've done something fairly bad here, so bad that I'm just going to erase this and apologize. Okay, so what did I do wrong? What I did wrong was, I'm going to write it in green. Say, that's not the formula, is it? That right there, f primed of g of x in our integrand. I left off the prime mark on the f. Now we're ready to talk about it. Okay, so what's left in our formula or integrand above? Well, what is left is going to be the derivative. f primed of whatever. Well, f primed of whatever, the only thing left is that fifth power, and math's favorite generic variable is x. Second favorite generic label for a function is, and as sort of a letter variable we use is f. Anyway, beside the point, f primed of x equals x to the fifth. How would I find f of x, the parent function that has that as derivative? Well, integration or anti-differentiation. We would just integrate x to the fifth power, and we'd get 1/6 x to the sixth power. So what did we do? We took our known thing, which we identified from above, and we figured out that. The rest of this, g of x, was also just identified from it. So we could just pick out the things I just highlighted, and all we needed to do is calculate that guy. And so the question becomes, we want the original function. We want the original function. And what is the original function? Well, the original function would be f of g of x. So what is f of g of x? Well, f is 1/6 times whatever to the sixth power. And then g of x is that x to the third plus x guy. And so this is our guess. And so our guess, we have come up with a guess that this is potentially the answer to our integral. 1/6 times x to the third plus x raised to the sixth power plus c, because we know this thing is an indefinite integral, is equal to the indefinite integral of x to the third plus x raised to the fifth power times 3x squared plus 1 dx. Let's check if this works. So we will check. And so to check that, we'll take the derivative of 1/6 x to the third plus x raised to the sixth power plus c. We'll take the derivative, and what we should get is the integrand. So 1/6 out front. Chain rule here, we're going to take the derivative of the outside guy, so drop down that exponent, subtract 1 from the exponent, leave the inside guy the same, g of x, multiply by the derivative of the inside guy, g primed of x, so we're going to multiply by 3x squared plus 1, and sure enough, we have the integrand, and we've done it. Now, this is not at all the way to do this, but it's kind of nice to see that we did it. We came up with the right answer just by kind of reverse engineering it. But hopefully the point of seeing that was to say, oh, this seems like it could be really hard. And so there is a much, much, much better way, and that's substitutions. So let's do it. But before we do it, I want to write one thing. And the key to substitutions. How do you know when you should use a substitution? The key idea is to get used to recognizing when you can see a function and multiplication by its derivative. And it's absolutely okay to think, okay, I'm going to just look for a function and its derivative. Maybe that function's hidden inside something. Maybe it's not. This is just a key, the idea that a substitution is going to help me, because oftentimes if you're dealing with the chain rule with differentiation, you're going to see the function and its derivative. And so if we're trying to reverse the chain rule, then we need to see a function and its derivative in our integrand. So here's the method. Let's just take a look at the general method for this. So again, the key is to find a function and its derivative. So you better find a function and its derivative. Then we're going to make some substitution. We're going to let u be the function, and then du dx will be its derivative. And that's just doing regular old differentiation and keeping track of our differentials, which we know we can sort of algebra. So then you're going to make these substitutions and integrate with respect to u. Once you have your answer will be in terms of u, which is not great because your question was in terms of x, presumably, or some other variable. And so you have to back substitute your original substitution so that you get your answer in terms of the variable with which you were interested in. That's a lot of words and hopefully makes some sense, but really is best if we do an example to see it. So I titled this slide Substitutions /u substitution. That's often because different texts call it different things. It's very, very common to use the letter u as the variable for substitution, and hence oftentimes substitutions are referred to as u substitutions. So let's revisit this exact same problem. And so what we're going to identify is we're going to say, okay, I just found a function and its derivative. And so what we want to do is we want to let this function be u, and then its derivative is going to be du. So first things first, let's make our substitutions. 1, u is equal to x to the third power plus x. And then we are going to take its derivative. Du dx is the derivative of this function, derivative of u with respect to x. So 3x squared plus 1. Now we know we can sort of algebra recklessly differentials. So we can put this in what I'm going to call differential form. So by multiplying dx on both sides, dx on both sides, you will get du is equal to 3x squared plus 1 du. We could put a set of parentheses around there if you like for a little more clarity. And check it out what I'm sorry, I'm making mistakes left and right here with my variables. Let's start again and say it correctly. So if you took this expression on the left, du dx equals 3x squared plus 1, and multiplied both sides by dx, you would get du times the quantity 3x squared plus 1 dx. And that would be, we're going to call this the differential form. And notice this differential form is exactly the same as what we had in our original integral. And so what we're going to do is we're going to replace that thing with du rather. Because if it's the same thing on the left of a equal sign, we can replace it with the other side. So to do that, step 2 was to substitute in. Sub in our u stuff and then integrate. Okay, so our integral was integral of x to the third plus x all raised to the fifth power times x to the third plus 1. X to the squared plus 1. And we're going to make some u substitutions here. And so our, u is the same thing as x to the third plus x. So we're going to replace the entire expression of x to the third plus x with u. And now, highlighted above, we have, I'm going to double underline it, its derivative. Well, I can replace that entire expression, 3x squared plus 1 dx, with just du. And now we have an integral in terms of u, which is a basic power rule that we can integrate with respect to u. And as usual, WRT is with respect to 2. So u to the fifth power, integrate 1 over 6, u to the sixth power rule. Add 1 to the exponent, multiply by the reciprocal of the resulting exponent. Now this is an indefinite integral, so don't forget plus c. And now, wait a minute, our answer can't be in terms of u if our problem started out in terms of x, and so we are going to back substitute. And so when we do that, we say that, okay, 1/6 times u to the sixth power, u is not what we're interested in, but u is the same thing as x to the third plus x. And so we're going to undo that substitution and get 1/6 times the quantity x to the third plus x plus a constant c. And we've did it. We have done it, rather. I'm sorry. This is the same thing we came up with when we kind of reverse engineered the chain rule the manual way. So to close out this introduction and a couple of examples, I just want to make one last little comment here. And that is kind of a hint and a just general strategy. If it is hard to spot your function and its derivative, so I'm just going to put if it's hard to spot your u, and we want u equal to the function and its derivative with a derivative present in our integrand. So if it's hard to spot your u, often our thing we're going to substitute, often our u is the, quote, inside function. And looking back at our example, what I mean by inside function here is, well, our u was the thing that was hidden inside of the fifth power function, whereas the other bit, 3x squared plus 1, was kind of outside. It wasn't hidden inside of anything. So that's just kind of a general tip and strategy as you're starting to try these problems. And we'll talk about more in some examples that are coming up.